the suggestions are very helpful and we'll try to implement them. I want to mention that the TAs from last year, led by Graham Holt, won the CS department's Best TA Award in our department meeting last Wednesday. And actually TAs from this class have won the Best Teaching Award for the past 6 years for teaching this class. So I think we're doing well with that, and we always can improve and appreciate your comments and suggestions. So thanks. So today I want to talk about functions and types. And to do that, I'm going to share my screen and we'll work with the document camera for a little bit and do some math and computer science together. Let's see if that works. I'm going to migrate to the other side of the room and we'll see how that works for everybody. Okay, please tell me if you can see me and hear me and see the document on the camera.
You are all good.
Yeah.
Thank you, I appreciate it. Thanks for the help. So I want to pick up where we were last time. We did some really amazing things in lecture last time, even having some short assignments. And so we did some things that were kind of like this. Let me get rid of that mouse, which drives me bananas. So we were able to introduce some notions to talk about functions that could be used to tell us the size of things. So for example, we could say things like, this definition from before, a set S is countable if there exists an onto function, which we'll call a surjection in this lecture, from the natural numbers onto S. And using this as a tool, we did some quite interesting things. We showed that the integers and the rational numbers are countable, the real numbers are not. We also looked at functions and concluded by realizing that there exist mathematical functions that are uncomputable, in other words, cannot be programmed. So kind of a remarkable series of things to do in one short lecture in only part of the class. And so our picture of this might look something like this from before, is that there are many, many, many real numbers in some set like this, and some subset of these are the integers, and some slightly bigger set, perhaps, you might think, the rationals, but actually these are the same size, but there are many real numbers that are not rationals and are not integers. And amazingly, we had a similar looking picture for functions. If you imagine the set of all functions looking like this, this is all mathematical functions. And a strict subset that's much smaller is all computable functions. And moreover, we actually gave you examples of these things. So you know that there are some real numbers here that are not rationals. We proved, for example, this is the square root of 2. And we also have some numbers like pi. So there are lots of real numbers that are not rational. The reals are uncountable. But the set of all mathematical functions is uncountable, but the set of computable functions is countable. So pretty interesting. And it leads us to some questions about, well, what do we need to learn about functions to really understand what's going on here? And there was a request, which I will honor next week, to try to give you some intuition about how can it be that, for example, for the numbers, there's so many real numbers and so many fewer rationals, even though they're both infinite. So I will tell you next Monday, a week from today, we'll start talking about what are called the algebraic numbers that actually fit between the rationals and the reals and form the basis of the fields of algebra and geometry and mathematics. But back to computer science, the main reason we're doing this now is we need a more sophisticated view of functions than we had in lectures 1 through 12 as a model to get to our goal of understanding Turing reducibility. and this will be lecture 19 in the current lesson plan. So we need to know a bit more about functions in order to get there. And this is important because this is essentially a recipe for proving what's the hardness of problems, what's computable and what's uncomputable. Now, at the same time, we have other things we're interested in doing. So types are ubiquitous in computer science and the field of programming languages. So while they are very powerful, they may be a bit mysterious to you. What exactly are types? We're going to learn that today, at least in some form. And another thing we're going to try to talk about today is what does it mean for two sets to be equivalent or similar in size or structure? We talked a little about that in recent lectures, like basically a week ago. But I like to be more precise about the notion of two sets that might even be infinite having the same size or the same structure. So that will be sort of important. And that concept is sometimes called isomorphism, which is Greek for same shape, also same size. Also a term in biology, iso, same, morph, shape. You can always remember this by thinking about bunny rabbits. So in the systematic biology classification of bunny rabbits, you have lagomorphs. And these are separated into hares and bunnies or rabbits. Lagomorphs means hair-shaped from the Greek. Morph, shape, lago, hair. The difference between hares and rabbits is that rabbits have altricial young and hares have precocial young. So why do I bring up biology here and these strange words? So this more sophisticated view of functions we're developing today and also on Wednesday, it's going to give us the ability not only to do Turing reductions, but we'll have the ability to classify them, classify problems and classify programs the same way biologists do for animals and prove new things about them. So we want to classify the problems by their hardness and also make the concept of types clear. What exactly are these things? Or clearer at any rate. So for that, I want to give you a more sophisticated view of functions that we can think about today. So let me preface this by saying that the concept of a function is something that you're already, somewhat familiar with. You've seen many times already. And I don't think it's necessary to remind you that, how central it is to all of mathematics and computer science. And Scheme models the computable functions in a very, very nice way, which you're already learning about, maybe even your master's up at this point. So in mathematics and also in computer science, a function is usually thought of as a rule, if you will. It's a rule that assigns to each element of a set A some member of a set B. And you could think of the function as being drawn like this, function f. So for example, in calculus, we might have something like f of x is equal to x squared plus 1. And of course, we can nicely model this in Scheme by saying define f to be lambda x plus times x, x1. And they're really the same object. One gives you declarative knowledge, the other gives you imperative knowledge. And in many fields such as calculus, even analysis at times, one does not even really mention the sets A and B here. We don't mention them explicitly, we basically agree to take A to be the set of all real numbers for which the rule makes sense, that is, and B to be the set of all real numbers that could be the output, so to speak. So in computer science, the sets A and B are called types. And in mathematics, they're called the domain and the range of the function. An example will help here, because this is a little bit abstract. Let's contrast the CS versus math view, although they're fairly unified, and have a little function here that does something. So we'll have a function f that takes in a thing of type floating point, FLOAT, and returns an integer. Those are the types. And it's defined by the rule f of x is equal to the floor of x squared. In other words, the smallest integer, right, the integer that's underneath x squared. And of course, we can encode this very nicely in the lambda calculus and be more explicit and say this is lambda x, which takes in a type, say, number, like this. And it's going to compute floor, which is a scheme function of times x. And there's our function there. And the mathematical way of notating this would be the function f, which takes in a real number. Notice real numbers are not really floating point numbers, but they're kind of, floating points are a model for the reals. Takes in a real number, gives back an integer, and we'll use this notation here sometimes. X maps to the floor of x squared. So this notation here is exactly equivalent to this notation here, and you may use either one. I personally like this one, but certainly they're both correct. Let's take a look at this function to make sure we understand it. You could think of x as being a series of pairs or even a table that looks like this, just to make sure we're on the same page. X and f of x. It tells you a rule that assigns values f of x to each x. So if we had here 2, f of x would be 4, 2.5 would be 6, 3 would be 9, 3.5 would be 12, 4 would be 16, 4.5 would be 20, and so forth. Even if the table is infinite, it's still well defined. So there are some interesting points here that are worth noting. So in this definition here, especially the CS definition here, f can take as input any float. And the input type is sometimes called the domain of the function. Now the result of f is an integer. So and this is the output type or range, you can see here. Now, a key point is that f might not cover the entire range. In other words, f might not be onto. And you can see that was very important in our discussions before, because our discussions of various properties like countability relied on whether or not a function was onto. So here's a question for you. Either in the CS case where we have floats going to ints, or in the math case we have real numbers going to these integers here, a question as a warm-up is f onto by our definition? What do you think? Does f cover the range?
No.
That's correct. Why?
Because if you apply f to the codomain, you won't get back all the values in the domain, I think.
Do you mean f inverse to the codomain?
Yeah, f inverse to the codomain, you won't get back all the values in the domain.
Yeah, I think that's certainly true. We could also use our definition directly. I mean, that's absolutely right. One way to think about it is that there are elements in the range that are not hit by this function. So this function only hits the non-negative integers, right? So it can't ever hit the negative integers. So clearly look at this, there are going to be integers that are negative in the math version or the CS version. So no, it's not onto, because there exist negative integers you can never get to because it has an absolute value in there. Same argument as yours. I just picked a way of expressing it as elements. So we have a notion of the domain and range, which we'll define a little more formally later, but we can already define the notion of the image. So f of r is equal to f of x for x in R is called the image of f. And to express what you said a minute ago, the issue here is that we have which is z, because it only hits the natural numbers and 0. So in general, you have the situation where the range looks like this. In this case, you can see the range is all the integers, and you might have the case rule by saying that F maps the domain like this. We can be more precise about this, but that's the basic picture we have here. So here's the way of thinking about this. F has to be defined for all floating point numbers, or in the math version, for every x that's a real number. But there's no federal law saying it has to be able to output any integer, right? That's just not required here. And in general, we have this case looking like this, that the image of a function, the image of f in this case, is going to be a subset of the range. So it's always going to be true. It's generally going to be a strict subset. So only for onto functions do we have equality. So for an onto function, one way of thinking about this is we have the image of f is equal to the range of f. Okay, and you can sort of see that from this picture here. This is the domain, which in this case is the real numbers. Here's the range, which in this case is all integers. And here's the image of f, which is equal to the natural numbers starting at 0. So in general, we're interested in the relationship between these sets. And so now we see what types really are. Types are everywhere. They're fundamental to CS and programming languages, and they're in math everywhere, really at the heart of mathematics. Okay, so we have an idea of what types are getting to be now. We still don't really know what functions are, except for this table sort of expresses the idea that you have these way of assigning things, and you can think of these as pairs, which is the right way of thinking about it. So we actually kind of backed into this a little bit when we talked about a so-called proof of integration by parts. And many of you engaged this question rather strongly, which was delightful for those of us on the staff, especially me. And you pointed out that functions in general, especially in things like calculus, look like this. So we have points here x being taken to points here y, and you can think of this plane as being pairs x, y. This is a Cartesian product, and functions sort of look like something like this. So there's only one value for every x assigned by the function. So this would be a function where something like this would not be a function. Here I have the same pictures on the axis x and y, and I might have some crazy thing that looked like this. This is not a function. Oh, slide it up a little bit. So we have this notion of domain and range, which corresponds to these types. And we have this notion of a function, namely that you could have at most one y value for every x1 on the graph of the function. So this would not be a function here. This would be a function. And I've already given you a hint about this, is that this entire plane is Cartesian products. And so in some sense, in order to get a function, we have to start with a Cartesian product and restrict it appropriately so that we get things that look like this and not things that look like this. So the domain is big. Basically the domain and range, when you cross product them, give you this enormous thing like the plane. We want to get subsets of it that look like the thing on the left, not like the thing on the right. And for that, we need to have some definitions, and then we'll really know what mathematical functions are and be able to use them. So for what we need to do next in the class, we need to be quite a bit more precise than this picture about what a function really is. So let me confess to you that mathematicians actually think of functions in the way that I just described. But the definition we use is much more exact or precise. And for that, we're going to define something called a rule of assignment, and we're going to use it. So I'm going to write this down, then I'm going to spend some time helping you parse it. It's really not that complicated. Again, think of this dilemma we're trying to solve as if we have a general situation where I have the domain here and the range here, how do I restrict functions so they look like this and not like that? Obviously, I've drawn the Cartesian product of the domain and range like this, which is the right idea, but somehow I have to restrict what the function can do. And that will be a subset of the Cartesian product. So more precisely, it'll be something that looks like this. So I'll write this up, and then we'll help parse it. So given two sets, C and D, a subset called R of the Cartesian product, C cross D, is a rule of assignment or ROA, if what? If we have the condition that if the pair C comma D is in the rule of assignment and C comma D prime is in the rule of assignment, then D must be equal to D prime. Okay, so let's help parse this in words, but this mathematically is what we need. By the way, this term ROA is only used in this class. You'll never see that. It's a shorthand, but rule of assignment is used universally in mathematics and in computer science. So let's be more precise about what a function is really. So we're going to define a rule of assignment. So what is a rule of assignment? A rule of assignment is a subset, little r, of the Cartesian product C cross D of two sets. And it has the property that each element of C appears as the first coordinate of at most one ordered pair belonging to R. And that's what this says here. And thus this subset is called a rule of assignment. So we think of little r, the ROA, or rule of assignment, as a way of assigning to each element little c in C, and the element of big D, which is called little d, for which C comma D is in R. So I'll write that down as intuition. R assigns to each element, little c in big C, the element D in D, for which the pair C and D is in the relation. Okay, now some examples will help here. Let's do a couple of them, of both things that are rules of assignment and things that aren't. So let's do an example here. Two ways of writing this example. We could write this as the set of pairs x and x squared in Z cross Z. We could also write this as the set of pairs x, x squared, and just say that x is in Z, which is fine. And obviously this is a subset of Z cross Z. So this is a rule of assignment. In fact, it encodes the function square defined on the integers. And I'll just write that down. Let's look at something that is not a rule of assignment. So let's look at the set of ordered pairs x comma y. And these also lives in the Cartesian product of the integers with itself, such that x is less than y. So this is not a rule of assignment. It's what's called a relation. Namely, it's the less than relation. How can we prove that? Well, this particular set contains both 1, 2 and 1, 3 are both in the rule of assignment. And for that reason, it can't be a rule of assignment because it violates this property here. So again, the rule of assignment is our way of using our Cartesian product to encode the intuition that our rule should assign to each element of the domain, C, the element of the range, D, for which C comma D, the pair, lives inside our rule. So now we can be relatively precise about what a domain and what a range really are for a rule of assignment. So defined, given a rule of assignment R, the domain, which you can't spell out, but I'll just write it like this, domain of R is equal to what you kind of expect it to be. It's equal to all points C such that there exists some point D such that C comma D is in the rule of assignment. And the image of R is just the other way around. It's all points D such that there exists some point C such that C comma D is in R. So the domain and the image come essentially from projecting the rule of assignment onto the x-axis and the y-axis. That's pretty good. So finally, we can put these together to talk about what a function really is, and then we'll use this. So a function is a pair R comma B, where R is a rule of assignment and B is a set such that the image of R is contained in B. Remember, the image is defined right here. And we write it as F goes from A to B, where A is equal to the domain of F, which is defined right here. And we write the rule as A goes to B, such that the pair AB is in the rule of assignment. And finally, B is called the range of F. So this is what a function actually is. So it helps to parse this in words a little bit. Let's go back to our definition of domain. The domain of a rule of assignment R is the subset of C consisting of the first coordinate of elements of the rule of assignment of R. And the image set of the rule of assignment R is the subset of D consisting of all second coordinates of R, formally stated like this. And we can also parse our definition for function. So a function down here is a rule of assignment R together with a set B that contains the image set of R. So the domain A of the rule R is also the domain of F, which is what we want. And the image set of R is called the image set of F as well. And B is just called the range of F. It just has to be bigger than the image set. And we write it in this notation here. And we think of this as being F is a function from A to B. So one sometimes visualizes this as sort of a geometric transformation, physically carrying the points of A to the points of B in this fashion. So this tells us what a function actually is in this sense. So we'll come back to the definition, but some examples and usage of this will be very helpful. But now we've actually been able to say what functions really are, which is very useful when we're talking about what things can be programmed and which things cannot. Let's do some examples of functions and using them, using our new notation.
Professor Donald?
Yes.
There's a request in the chat just to go over the definition of image one more time before going on.
Absolutely. Great question. Let's do that. Okay. So if we look at our ordered pairs that correspond to the rule of assignment, it's pretty clear that the C's are going to be something like the domain and the D's are going to be something that lives in the range. And this is a way of basically just projecting onto the second coordinate. So the image of a rule of assignment R, remember R is a set of ordered pairs, is all points that are in the range such that there exists some point in the domain that maps to that point. So we parse that as all points D that are in the range, such that there exists some point C that's in the domain where we have C comma D is in the rule of assignment. So again, if you think of the functions as being ordered pairs here, so we have C like this and D like this, we're interested in knowing when we can, which points we're actually hitting here. So if you look at things that would be in an actual, say, function, each one of these is a pair, C comma D. And so the way to think about this is look at each point C comma D, and we're going to just look at the D coordinate of that, and that's going to be the image. If we just look at the C coordinate of that, that's going to be the domain. Does that help?
Yes, thank you. Perfect.
Sure, sure. And thank you for asking. Great question. And I think I'll do some examples that will help with this a little bit. Using this notation, which we'll come back to, we can write, for example, f from R to R, so it takes in a real number, such that f of x equals x squared plus 1. We can equivalently write this as f from the real numbers to the real numbers that send little x to x squared plus 1. Example of a function. And either of these notations are totally fine. So you may wonder why we make a distinction at all between range and image. And the reason is that we want the types to match so we can compose functions. So given this, we can talk about composing functions and how this is going to work. So you've seen the function compose, and we've done this a little bit, but let's talk about what it means for the various domains and ranges and types to match up. So I'll talk about composing functions up here. So definition. Given functions f from A to B and g from B to C. So again, in computer science, you could think of these as types. Input type, output type, input type, output type. In mathematics, this is domain, range, domain, range. And notice that I have the range of f match the domain of G, which is essential for this construction. We define the composition G circle F of F and G as the function G composed of F from A to C, defined by the rule A goes to G of F of A. Let's draw a picture of this. So here we have these spaces like this, and we have a function f like this, and we have a function g like this. And let's take a representative point here, A. Let's take A and we'll f it. When we f A, we get a point B like this. And then if we apply G to that point, we get this point here, which is G of B, which is simply equal to G of F of A. So this is the composition or composite of two functions. And the key thing here, key criterion, is that the types have to match. So we have to have this to work. We must have that the range of F equals the domain of G. And this is what type checking is, something you've heard about quite a bit in computer science classes. Now, what is this composed beast? Looks a little bit strange in some ways. And can you really compute it? Well, it turns out we've seen it. It's exactly what we've seen in the lambda calculus. So G composed with F is exactly equal to compose FG, at least for computable functions, where, and of course you've seen compose in class and even on midterms, we define compose as follows. Compose to take in two functions, F and G, and we're going to return a new function, which is a function of one parameter X. And what does it do? It applies G after Fing the X. Certainly a friend from one of the problems on the midterm and some of our assignments. Now, by the way, if you've done any Zoom calls, you know that I can't see the chat when I'm sharing my screen, but if you have any questions, please ask a TA to ask them if you're shy or if don't have good connection, or you can interrupt me by speaking at any time. So I'm more than happy to take questions on this material. We can answer them all. I can see the chat when I'm not sharing the screen, but when I'm not, Zoom doesn't let me do that. All right, so let's do an example here. Suppose we have G composed with F is equal to compose of the two functions lambda x times xx and lambda x plus x5. So it's pretty easy to see what's going on to get started here mathematically. We have that the function f is a function that takes in a real number and gives back another real number, and it maps x to x squared. And similarly, we can see that the function g is a function that takes in a real number, gives us back a real number, and it takes x as input and gives us back x plus 5. By the way, these symbols here, this is long right arrow in LaTeX. This is the symbol \maps to. And it's distinguished by having this little thing on the front here. It's telling you where the elements map to. So now we know what F and G are. And we know that G composed with F has to be a function from R to R also. But what's the rule? What do I write down here? What should this be?
X squared plus 5.
That's correct. So now we're starting to understand what's going on here for sure. Now, I want to note to you that if we compose these in the opposite order, we get something that's very different. So F composed with G, which is equal in lambda calculus compose in the opposite order here, just compose these backwards, I'll just write it out. Lambda x plus x5, lambda x times xx. So notice I've just reversed the order here. I get something else. I now do also get a function here, f composed with g, that goes from the real numbers to the real numbers. But the rule of assignment is very different. What's the rule of assignment in this case?
X plus 5 all squared.
That's correct. Very different functions. And you can see this by looking at individual elements, the notation we might have here. For example, suppose we take G composed with F and apply this to 4. What do we get?
$21.
21. On the other hand, if we take F applied to G and apply this to 4, we get what?
81.
81. So the order of composition matters a great deal, but we can compose functions. Okay. Now, in order to get a feel for domain and range a little better, we're going to introduce some new terminology to help us classify functions. And this will include the terminology we had before for onto, but we'll also have two other beasts that will be friends with onto. I'm going to give you a little table that will help you in all your math classes and your life henceforth. So the term onto, which we will review, of course. There are other terms too. So basically, mathematics was a little bit disorganized. It was very sort of, you know, a little bit informal. Think of, you know, casual British food, because a lot of British mathematicians, casual Italian food as opposed to formal French food. And basically what happened is that French mathematicians under the leadership of Jean Dieudonné formed a collaborative called Bourbaki, which was a pseudonym, and they axiomatized a lot of mathematics and made it quite rigorous. And they used terminology that's in French for this, and we use that terminology to this day. So onto is called a surjection. Into, which I shall define, is sometimes called one-to-one, but we call this injective. And there's a term that's both of those together called bijection, sometimes called one-to-one correspondence. And these terms are completely equivalent, and you'll see them even in this class used. Now, I don't like the term one-to-one because it can be confused with one-to-one correspondence. So I don't like that term, even though it makes some sense. And I prefer the French terms, and you can imagine getting some French language credit for this. Again, these come from the French term, I said surjection, but the adjective would be surjective. In French, this is bijective, injective, surjective, bijective, injective, surjective. And we'll prefer these terms here, but you will hear onto for surjective, into for injective. We won't use one-to-one correspondence very much, but it is useful for talking about the size of sets. So let's talk of these. I'll do surjective first, which review that, then do the others. This is review, the first one, define a function f from A to B is surjective. Again, French, surjective. If B is in B, implies B equals f of A for some A in the domain. Now let's look at this injective thing. So a function f from A to B is injective, in French, injective, if f of A equals f of A prime implies that A equals A prime. Let's do some diagrams of these things. I want to again remind you what surjective means, or onto. This means that if we have a function that looks like this is our set A, this is our set B, this is our function f. We're illustrating surjective. This is the case where the entire domain is covered. So B is equal to the image of A. And what we're saying here in these runes is if we take little b in B, there must exist some point A such that when we f the A, we get B. And that's true for any points. So B is equal to the image of A. Now the case for injective is also interesting to visualize. If f of A equals f of A prime, then A equals A prime. This is often visualized as follows. I'll draw my set A like this and my set B like this. It means that if A and A prime are distinct points, then when I F them, I get two distinct points over here. So the size of the image of A is exactly the same as the size of the image of B. Now, a marvelous thing happens if both these things happen at once, which is called bijection, in French, bijective. We say F is bijective if it is injective and surjective. So this is really a marvelous thing. Let's do some examples and then come back to this. I want to come back to what it means to be bijective in some sense. So let's have an example here. I'll call this guy F2, why not? From the integers to the natural numbers. And this function sends x to the absolute value of x. So let me ask you, is this function onto? And is it one-to-one? Oh, I shouldn't say one-to-one, I should say injective. So what do you think? Is this function onto? Function F2 sends an integer to its absolute value.
Mm-hmm.
What do you think? I didn't quite parse that. Do you think it's onto?
Yeah.
Yes, it is onto. What's the argument that it's onto? Well, every integer that's a natural number is covered actually twice, right? It's covered by itself and it's covered by its negative. What about injective? Is this function injective? Do 2 points in the domain have unique images in the range?
No.
No.
No, you're right. What's an example here?
-1 and 1, 1 and 1.
Yep, absolutely. -1 and 1 both map to the same thing. So it's onto, but it's not one-to-one. Very good. Let's look at F3. Here's a function from the integers to the rational numbers, and it takes x to x over 2. Let's ask this. Is this injective? And is it onto? What do you think? Is this injective?
No.
Are you sure?
Yeah, wouldn't 4 over 2... Oh, no, wait, that's wrong.
No, it's good. We have to work it out.
Yeah, I guess it is injective because for each x, there's a unique y.
Yeah, that's correct. I mean, let me just tell you my reasoning about this. Suppose we have f of a equals z. Let's use the definition here, right? F of a of prime, and let's say f of a prime equals z, right? For some rational. Well, we can say by looking at the structure of the function that a is equal to 2z, and looking at the structure of the function that a prime is equal to 2z. And clearly 2z equals 2z, so a equals a prime as desired. So there we go. So it is injective. What about onto? Is this function surjective?
Mm-hmm.
Why do you think it's surjective?
Oh, wait, it's not surjective. The image is a subset of rationals.
Yeah, that's correct. Can you give an example of a rational that's not hit by this function?
1 over 3.
Yeah, 1 over 3, counterexample. Very good. All right, let's look at a fourth one. This is discrete math, but infinite. Here's finite discrete math. How about the function that takes 1, 2, 3, a discrete set, to the function 100, 200, 300. And the rule of assignment takes x to 100x. So is this function injective?
Yes.
Yes, it is. Is this function onto?
Yeah.
Yes. So we conclude this is bijective. So this is an interesting thing. When you have bijection, it means the sets are very, very similar. It means they have the same size. It means all sorts of marvelous things. So I'm going to state something that you all should try to prove, but if you can't prove it, I'm happy to help you do it. Basically, if you have bijection, then we have a marvelous situation. So if f from A to B is a bijection, I'll slide this up just a little bit, but we can come back if you need the definition onto is a bijection, then A and B have exactly the same size, in this case 3. And this definition works even for infinite sets, as we shall see. And bijection is the foundation of isomorphism or equivalence in mathematics. So every isomorphism or equivalence in mathematics is a bijection. And now you can see the terminology why they sometimes call bijection one-to-one correspondence, because it means everyone in here corresponds to a unique element here and vice versa. And moreover, there's a marvelous property that holds, and I'm going to state this without proof, but I hope you will prove it. If you can't prove it, you should talk to us, or maybe we'll answer questions in recitation, because it's a very important thing to understand. So if f is bijective, then there exists an inverse function that goes in the other direction, from B to A. And I think you can clearly see in this case that the inverse function takes the value in y and divides it by 100 to get the value in the domain. Now, how is this inverse function defined? F inverse of B, for B being a point in the range, is the unique element of A such that f of A equals B. So your task is take this claim that if f is bijective, there exists an inverse function, and argue, based on your knowledge of functions and sets, that the inverse is well defined, namely that there is such an A, and also that A is unique. And you can prove both of those properties using the properties of surjection and injection. Okay. And by the way, I don't mean to leave you in the cold. If you are stuck, we will absolutely show you the proof, but try to do that one yourself so this isn't all passive learning. Okay. Now, let's do an application of this, one that we'll need to understand and some detail for Wednesday's lecture. So claim. Suppose we take the natural numbers and their Cartesian product. I claim this is countable. How do we prove this? Well, we can prove this by dovetailing. And in fact, Kyle and his recitation and some others did this in last Friday, which is really great. And there's a sketch of the argument there. So you write down a table, just as we did when we counted the rationals, and you have to get the ordering and the numbering right. But basically in the same way that the rationals are countable, we can think of the set of all pairs, A comma B, where A and B are both natural numbers, will be countable. And I think you can do this proof by dovetailing, having seen my proof. And you should try that. But I want to show you a way to prove this in another way that uses our newfound understanding of injective, surjective, and bijective functions. So proof one, dovetail. But one proof is never enough for a mathematician, and I want to show you some new techniques. So proof number two would look like this. By the way, I have not proved this for you by dovetailing. I have claimed that it's essentially a modification of our proof that the rationals are countable. And I've suggested that you prove it yourselves. But this next proof will be one that has all the steps. So a second proof, a different kind of proof, that uses a property of injective and surjective maps. So I'm going to start by saying the following. One, I claim there exists an injective map G from the natural numbers cross itself to the natural numbers given by taking the pair P comma Q to 2 to the P, 3 to the Q. Now, what you should do, show G is injective. Why should this be true? Well, because this is a unique factorization of products of prime numbers. But you have to actually show that it's injective directly. Let's assume that you've done that. So I'm giving you little things to think about so you understand the lecture. One is to prove that if F is a bijection, that it has a well-defined inverse. Second, show the natural numbers squared are countable by dovetailing. Third, look at my function here that takes a pair PQ to 2 to the P, 3 to the Q. Show that this function G is injective. Let's suppose that you've done that, and I'll build on that now. I'm going to be slightly more general here. I'm going to say let G be some function B to N. So this is an injection from any set B to the natural numbers. And obviously in our application here, we're interested in the case where B is equal to the natural numbers squared. But I'm going to prove this for absolutely any set at all B. And we'll just have to remember that in our case, we're applying it to N cross N. I won't use any properties of the natural numbers to do this. So we wish to show B is countable. So notice this is different from what we did before. Before we showed things were countable by having a surjection from the integers onto the set of interest. Here we're saying if there's an injection from the set of interest into the natural numbers, then the set of interest is countable. So the picture looks something like this. We have a set here B, which of course in our case is the natural number squared. But it doesn't matter what it is for the sake of this proof. It can be any set. And over here we have the natural numbers like this. And I have my function G, which I have claimed is injective, and you will prove that and show me your proof. Now I have this function here, and it's injective, 1 to 1. Now the image is going to look like this. This set here is the image of G. Now, in the case where the image of G is equal to the range of G, namely all of the natural numbers, we're done. But I'm interested in the interesting case where it's not. So let's go back to see why it might not be. Well, in the case where we have our function G as given here and B is the natural number squared, there actually are some points here that are not hit by that function. For example, the integer 5. So there'll be many interesting cases in which the image is smaller than the range. So here's my trick, and it's based on a mathematical fact that we're going to use and prove, which is this function here goes from B to the natural numbers. But every injection is a surjection onto its image. So if I were to define a new function that had a smaller range, namely just the same image, then it would be onto that set. So what I'm going to do is the following thing. I'm going to define a new function in order to do that. So my trick is I want to have a way to basically invert this function, so to speak, have a function from the natural numbers that covers this thing here. Because I know that if I had a function going in this direction, which I call h, and if h is onto, then I've shown that b is countable. Because my definition that I'm working with for b to be countable is there's a surjection from the natural numbers. So I'll pick some point here, b0. It can be absolutely anything. It doesn't matter what it is. It's completely arbitrary. And I'm going to define a new function, h, as shown, which is from the natural numbers to b. And I haven't used any properties of it yet. And h of n is defined as follows. So if this function is going to be in here, I'm just going to invert it using g. Otherwise, I'll send it to b. Let me be more precise about that. So I'm going to do this by defining a helper function here from g. So remember, we have this function g from b to n, which is an injection. So I'm going to define a function g prime from b onto the image of g. So in other words, it's exactly the same function, but now I have a function whose range is equal to the image. And of course, remember that the image of g is just defined as g of b such that b is in b. So what I've done here is I've started with g, and I've defined a new function that just restricts the output type to be the things that are actually hit by the image. And now I'm ready to define my function h. Notice that g has several properties. One, it's injective. By the way, what does it do? It just sends b to g of b, right? It's injective because g is, the parent function g is injective, but it's also surjective because the range is exactly equal to its image. And therefore, this is bijective. And therefore, there exists an inverse g inverse. So I'll define h to be equal to take g, inverse it. Sorry, I'm going to write this as g prime inverse of n. And this is what I do if n is in the image. Otherwise, I'll just send it to b0. So in this construction, what I do is I start off with a function that's injective from b to the natural numbers. And then I observe that if I define a new function that gets rid of all the stuff in the range that's not hit, namely I have a function g prime just goes from b onto the image. This function is a bijection. It's injective because it inherits that property from the original g. It's surjective because the image is equal to the range. And therefore, there's an inverse function, g prime inverse, that will take any point in here to a point back in b. So what I do in order to define a surjection from the entire set n is if it's in this image set, I just take g prime inverse. If it's not, like 5, I just send it arbitrarily to b0. But by doing this, h is a surjection. And because h is onto, therefore I've shown that n cross n is countable. Okay. So this is a use of our techniques to explain the range of things that we can actually prove. So remember that our standard definition of proving things are countable was to find an onto map from the natural numbers onto the set. In doing this, what we've done is we've been able to find another condition, they're actually equivalent. If we have a set we're trying to show is countable, we merely need to show that there's a one-to-one function from that set into the natural numbers. Then we can restrict that function to its image. That will be a bijection, which will have an inverse. If we want to then find a surjection of the natural numbers onto the set B, if it's in the image set, we just take the inverse and we travel over here. If it's outside of the image, we just send it to an arbitrary point B0. But every point in V is covered because it has to be covered by, every point in here is covered because it's covered either by points in the image set or by points that are going to be 0. So this shows that the product of the natural numbers with itself is countable directly. Okay. So at this point, I think a couple of examples before we close would be useful. And please ask any questions you might have.
I have a question concerning our use of G prime and G. Are they defined differently?
Yes, they are. I'll put this up here and I'll just do it. Well, I think I can do it like this. So G prime and G are defined differently. They have different ranges. So the rule of assignment is the same, right? The difference is here. So G has a range of all the natural numbers. G prime has the same rule, but it just goes on to this image. So all I've done is I've restricted the output type to be things that it actually can hit and not things like 5.
I see, yeah.
So the thing is, it's a little different from calculus where everything was about real numbers, right? And nothing wrong with calculus, we use it all the time. But here, in a function that has a different range, even in the same rule, is considered a different function. And this is the reason you can kind of get your head around that as a computer scientist is by saying types have to match. So here we've made the types match. So there is no inverse from the natural numbers. This is an injective function. There's no inverse because there are things that are outside the range like this. So what we do is we define a new function that has a restricted output type. Other questions?
What's the symbol next to the G prime inverse in the parentheses?
Here?
Yeah, to the right of it.
Oh, this is a minus. Let me write that a little more clearly. Yeah, sure. So I'll just write it on this side. I'm just repeating what's over here. So what's h of n, this function here? H of n is my surjection. I've now proved it's onto, which is what I want. So what is h of n? Well, if n is in the image of G, right? So we want to basically check that. So if n is in the image of G, sorry, let me just rack these. It's an image of G, then I can take G prime, I can inverse it, and apply that to n. Else, I just send it to be 0, which is my arbitrary point. So when you think about this is, G's image is this thing here. I restrict G to be a bijection onto its image. So if I pick a point here, I could just take G inversed to go back over here. But if I have a point outside, I send it arbitrarily to be 0, just so it's defined on the entire domain. Is that more readable?
Yes, thank you.
Good, great question. More questions?
Can you explain again the difference between the definition of G and G prime?
They have different range. So remember that when we have a function, let's look at arbitrary function. There are basically 3 things going on here. There's the domain, there's the range, and there's the rule of assignment. If you change any one of those, you get a different function. So to make it clearer in this case here, we have G, which is a function from n to b. And it doesn't matter what it is. It's just, we don't have to write down a rule of assignment for it. In contrast, G prime is a function onto some other set. Let's call this set F, and say that F happens to be equal to the image of G, which is this thing here. And I have to tell you what the rule is. The rule is just take n. Oh, I have it backwards, sorry. Let me do this again. So, function specified by domain and range and some rule here. Let's take our G. G is actually a function from B to N. G prime is a function from B to some other set, F, which we're going to call the image of G. So let's go back to our picture here and look at what that means. So G is going to take points in B and send them to the natural numbers, but it only hits these things here. So I define a new function whose range is equal to its image. And the rule for this is I'll take a point here, say X, and I'll send this to G of B. So the rule of assignment, what you do is actually the same, just the range is different. So this is like changing the output type of a function. So suppose I had a function that that you defined in a programming language to take in floating point numbers and spit out floating point numbers. But suppose you noticed that it was only hitting integers. You could change the output type to be restricted to be only integers instead. So by changing the range of the function, I actually get what's technically a new function, although they're quite similar. Does that help the question?
Yeah, thank you.
Sure, great question. More questions?
I had a question about the other points in the domain that's not in the range, such as that's not in the image, such as 5.
Yeah.
So you explained that we could just have like a function that takes all those points to an arbitrary point B, and you said B0. So would all those other points be pointing to the same element in B?
That's correct. It's just completely arbitrary. And the reason is that I'd like to leave them out, but the thing is you have, for a function, you have to have a defined value that everything in the domain goes to. So remember, I'm trying to get a surjection from the natural numbers here onto B, right? So to get a surjection, I actually have to have a function. I don't have a function if I haven't defined where those points go. So I can't use G inverse. I can't use G inverse to send them. And the reason I can't use G inverse to send them is that it's only defined in the image. So I have to define it arbitrarily. So I just pick an arbitrary point there. So this construction requires that B have at least one point, but that's not a very large assumption. Does that help? Does that make sense?
Yes, thank you.
Good, great question. Other questions? Let's do a couple more examples just to make sure we're on the same page of these domain and range kind of things. So let's look at an example here where we have F from A to B. So if we have some subset, say A0 of A, we can define F of A0 to be F of A such that A is in A0, which is a subset of B. And this is called the image of A0 under F. And it's very close to the idea of map in scheme. So let's look at an example here. Suppose I have F from R to R, taking X to X squared. And let A0 be the closed interval 2 to 4. And we can graph this as follows. We have a nice parabola. And down here we have 2 to 4 as my interval here. And these will get mapped via this function to an interval on the y-axis. And this interval on the y-axis is going to be the closed interval 4 to 16. So A nice example of how to do this. Now, it's often useful to relate this directly to how map works, and to see that you have this function already. So suppose instead of having these strange continuous sets, we let, in a second example, say A0 equal just the points 2, 3, and 4, which is a subset. And we define G to be lambda x times xx. And we do map G of A0. We'll get back the set for 9 and 16. And this corresponds to having our set, instead of being this closed interval, be just these points here, 2, 3, and 4, and we get back these points here. So map is a very powerful thing that's closely related to images. And we can generalize this to the case where A0 is equal to, say, the natural numbers, and we could do something like stream map G over the integers. And this is the image of the natural numbers under F. So in a very deep sense, for the computable functions, map and image are very closely related for things that are computable. Let's do one more example that's sort of a puzzle I'd like you to think about, and then I'll stop and take some questions here. And this is a puzzle that really bothered mathematicians for a long time, but now we can explain based on our theory of countable and uncountable functions. So let me define an open interval, say AB, of the real numbers to be all points x in the real numbers, such that A is strictly less than x is strictly less than B. So if you've seen real numbers before, this might look on my real number line like this, where A is here and B is here, and our open interval is all points in here, like you've seen in calculus. So this might be the open interval between 0 and 1. So consider now the function f, which goes from the open interval 0 to 1 to the open interval 0 to 2, like this. And it takes x to 2x. So let me ask you some questions. Is f onto, and is f 1 to 1? Or injective? What do you think? Is f onto? Who has an idea? So these are questions that I'd like to leave you to think about. If f is onto and into, then in some sense we have the counterintuitive result that the open interval between 0 and 1 and the open interval between 0 and 2 have the same size, which seems counterintuitive because you might think that there might be twice as many real numbers in the open interval between 0 and 2. And this is something to ponder. It's basically one reason why these very large sets are hard to reason about without these formal tools. That having been said, I'd like at this point to break. I'll stop the recording, and I'll let you all think about these questions. And what I would like to do is stay around to answer any questions that might come up. And I'm happy to stay with you for a little bit if you